So what we're going to do today is I would like to give you some information about open addressing, which is one of the two primary collision handling techniques with hash tables, and then talk about the next assignment, which is going to be a paper. And let me just give you little previews here. This week you have nothing to hand in for the rest of the week. So it's all, it's going to take a little bit of time, a little bit longer than usual to set up the concept of a balanced tree. So we're going to be doing a little theory for a while. And plus the next assignment is to start on your paper. So there's nothing to do written this week. So, okay, so the first thing is collision handling by open addressing. Now this is really different from what we did. Our method that we used for handling collisions was chaining, right? And what happened is when you get a collision, you would just put that in a linked list, and that linked list could be allocated from the heap, and so there was no possibility of the table actually overflowing. But with collision handling by open addressing, what happens is you literally use the cells in the hash table to store the key value pairs. So they are literally stored in the hash table itself. And what happens then is if you have a collision and you try to insert an element into the hash table and it hashes to an index that has already been occupied, then what you do is you look for someplace else in the table. Now, is everybody clear on that? You actually look for another location in the table, and if the next place that you look at is filled, you look for another one, and if that one's filled, you look for another one until you finally get one, and then you stick it in the table. So the precondition for this to work is that there is at least one empty slot in the table. If not, it's full and you have to punt. So does everybody see the idea there? Okay. So now, and we're going to look at three different ways to do this. Okay. And the first one is called linear probing. Now, linear probing is kind of like the simplest way to do it. And here is a little pseudocode algorithm for how linear probing works. What happens is we see here that the precondition is that the table is not full, right? And I'm just going to show insert. I mean, there's similar ones for contains, and contains is like insert. And by the way, we'll have to think a little bit about this, about how you remove. It's a little tricky. But let's just take a look at insert with linear probing. What happens is we see here that to insert key val, instead of just putting it in one place, and if there's a collision, just sticking it on a linked list, what happens is I gets the hash function of the key mod the table capacity. So that part's just like we did before, right? But now what happens is there might be a collision. So the logic is a while loop. So while table sub I is occupied and table sub I dot key is not equal to the key. You see, so what does that mean? That means that first of all, if it's not occupied, we don't do the while loop at all. Like on the very first round, the test is at the top of the loop. If table sub I is not occupied, we just go right ahead and do what? Table sub I gets the key value pair. Now, does everybody see that? Otherwise, what we do is we say, well, if it's occupied, but now you have to compare it with the key. So this is short circuit evaluation. So if table sub I is occupied, then the second test happens. But if table is not occupied, that second test does not happen. It's short circuit, right? But if the table is occupied, then you got to check the key to see if the key that's stored is equal to the key that we're trying to insert. Are you with me? And then what's the post condition at the termination of the loop? It's not the test, right? That's how the loop terminates. So what is not table sub I is occupied and table sub I dot key is not equal to key by De Morgan's law. Either table sub I is what? Not occupied, or equals the key, right? And in either case, you overwrite. You're either overwriting the key or you're putting the one in there. Yeah, question?
So not equals key is just to make sure that like we're not doing nothing at all.
No, no, no. Actually, that's a good question. The not equal to key, remember in a dictionary, if the key is there, we overwrite the value.
Yeah.
So that's what this logic does. Are you with me? In other words, if we hash it to a place and it is not occupied and the keys are equal, then we terminate the loop and table sub I gets the key value pair, which in effect overwrites the value with the same key.
Okay. Yeah.
Now, yeah.
Oh, yeah. All right, I get you.
Yeah.
Because it's full, but you're saying like, okay.
It's full, but
it has the same.
But it does have the same. Right. Yeah. Now, does everybody see how that works? Now, what happens is, can you imagine then if you get this has a tendency to have the value, the key value pairs with the collisions. It has a tendency to have them clump. Do you see what I mean? Because if you get it to a if you get a collision to one spot and then you look for the next spot down, and if we get a collision with that one, it's going to be the next one and the next one down, and anytime you hit a clump, you're going to like grow that clump. I don't know if you see what's going on there. You kind of grow that clump. So the second kind of probing is called quadratic probing. Now check this out. With quadratic probing, what happens is, now we have this two preconditions. First of all, the table is not full. Second, we have this precondition for what the capacity of the table is. And I'll talk about this in a minute. The second precondition is table.cap equals k, and k is a prime number, and k mod 4 equals 3. We'll see why that is in a minute. But check this out. Let's see if we can read what the code does. First, we have a local variable, j gets 0. Are you with me? And then I gets the hash of the key value, mod table.cap. Then I gets f of key mod table.cap, and then we save the index, the initial index of where it was hashed to. Are you with me? So index gets I. So index will never change from here on out. Are you with me? And then what happens is we have the same loop, because it's all the same. This is the same logic for open addressing. So it's the same test. It's while table sub I is occupied and table sub I dot key is not equal to key. And now what we do is j plus plus. So the first time we go through this loop, the body of the loop, what will the value of j be? 1. It'll be 1. And then I gets what? Index plus. Now what do we check? If j is what? It's odd. The first time through, it is odd. So what's the first place where we probe? I is what? Index plus 1.
Oh.
Well, it's index plus j times j, but j times j is 1 times 1. Are you with me? So the first time we hit it, we check 1 after it. If that one is a collision, then the next time through the loop, what will happen? J will get to be what? 2. I will be what? Index plus, now j is not odd. What is it? It's 2, so it's even. So it'll be I minus, but now it's going to be minus. So instead of, it'll check 1 down here, and then it'll check what? If that's a collision, it'll check 2. Yeah, 2 up. And then, are you with me? Above. And then next time it'll be what? If that's a collision, what? 9 down. And then what? 3 times 3 is 9. 4 times 4 is 16. We see why it's called quadratic probing. All of this mod what? Mod the capacity. 25. Yeah, does everybody see? And what that does, you see, that instead of just boom, 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 that like spreads out the, when you have a collision, it spreads out so you don't have that clumping. Lot better lot better performance with quadratic probing, yeah. Okay, so but now look, here's what's interesting about this. How do you know that by doing this pattern, boom, 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 you are eventually going to test, because what do you have to test in order for any kind of open addressing to work? You're going to have to guarantee that you're going to, each time you get a collision, you're going to check another one, but what do you have to guarantee the algorithm does?
Does it go outside?
Well, it can go outside because we're going to mod. But even with modding, so modding guarantees we're not going to go outside, but
you won't like repeat something? It'll still.
Well, repeat until.
It's right there.
Yeah, say it again.
It'll keep clumping at all those like values.
Well, in order. Yeah. It's not what I'm looking for. Look, in order for it to work, what do you have to guarantee? That it will eventually probe what?
Every spot.
Every one. How do you know it's going to probe every one? Maybe it'll repeat, maybe it'll hit something and then...
Oh, you make it a prime number of...
Well, now that's what the idea is if k is a prime number and k mod 4 equals 3. See, look, that's this precondition, table.cap equals k, and k is a prime number, and k mod 4 equals 3. If that's the size of the, if you choose your table capacity to be that, then you are guaranteed that with quadratic probing, you will hit every slot of the table after one round. This is really an interesting, you math majors, this is really an interesting prime number theory. Look at this. I'm going to give, let's take a look. What I have on this next slide are some prime numbers k such that k mod 4 equals 3. Now, do you agree that 3 mod, what's mod mean? Such that k mod 4 equals 3. Does everybody agree that 3 mod 4 is 3? 7 mod 4 is 3 because it's 7 divided by 4 is what? Remainder 3. 11 divided by 4 is something, remainder what? 3. 19, 23, 31, 251. Do it. 503. Do it. 1019 divided by 4.
Of course, I can see it.
Anyway, so these are all. So if your hash table is one of these or a bunch of other ones, I didn't put them all. I just put a few small ones and a big one, a couple of big ones. But if your hash table is like this, watch this. Let's assume that it is 11. Let's assume that you make your hash table size 11. So it's indexed from what to what? 0 to 10. Now watch, and let's suppose that that initial hash is 5. Now check this out, you guys. This is really slick. What happens is 5 mod 11 is 5, so that's going to be the first one. Now suppose you get a collision there. Then what are you going to do? 5 plus 1 is 6. Mod 11 is 6, right? Okay, so you're going to check one. And then the next time it'll be 5 minus 4, but 5 minus 4 mod 11 is what? 5 minus 4
It's 1.
It's 1 because you keep adding 11 until you get, right? Until you get the remainder. And then 5 plus 9 is what? 14, right? Mod 11 is what? 3. And then 5 minus 16 is some negative number. You keep adding 7 until you get, and that's what? 0. Actually, 5 minus 16 is what?
11.
Negative 11. And so mod 11 is 0. And look, so which ones are you going to check? You're going to check 5, 6, 1, 3, 0, 8, 2, 10, 7, 9, 4. You have done every single one exactly once. And so if that's the condition on the size of the hash table, you're guaranteed that as you do this quadratic probing, you'll go through and you'll test every single one. And it works not only for 5, or if the initial one is 5, if the initial one is 6, if the initial one is 7, you can run this through, and you'll see that every one is done exactly exactly once.
Yay.
That's pretty slick. A pretty interesting application of prime number theory from math. But anyway, this is one way to do quadratic probing. It's not the only way to do quadratic probing. You can have a different precondition and have different restrictions and have quadratic probing still work. And then the third and last one is called double hashing. So with double hashing, again, the precondition is the table's not full. And now what happens is double hashing means that we have two hash functions. All right? And so the first hash function, the normal one, is f of x. And then we have a secondary one. We'll call it g. And the precondition for this to work is that the table capacity is k. And this secondary hash function, g of key, and k are relatively prime. Now what does relatively prime mean?
Is that they're prime for each, like you can't use one to make the other using one?
Yeah, no common factors. Right? No, right? So if they're relatively prime. Now, and if this is the situation, then here's how double hashing works. So for, again, and this is just for insert, key and val, I gets f of key mod table cap. So that part's the same. Now what we do is we use that secondary hash function to calculate what is called the stride. All right? And now this algorithm looks suspiciously like which one? This looks just like what? This double hashing looks just like what? Linear. It looks just like linear, except with linear, it says while the table sub I is occupied and table sub I dot key is not equal to key, I gets I plus 1 mod. So, but here what do we do? The only difference is it's what? I plus stride mod table capacity. And where the stride comes from this secondary hash. So the stride is going to be different depending on the key, you see. So it's a double hash. You see, there's a hash for the primary one, and then there's a hash for the stride if there's collisions. But the stride itself depends on the key. It'll be different. Maybe it'll be 5, maybe it'll be 2, maybe it'll be 13, maybe, you know, maybe it'll be, you don't know. It depends on the key. So the key, it goes each time, you know, plus the stride, mod, the size of the capacity, but it's different for the different keys. So it's not always the same one that could have a tendency to clump, yeah.
How do we know that's going to, well, how do we know, like, there isn't a stride that's going to cause you to go in a loop and adjust?
Yeah, that's a good question. So you have to design G, you have to, I'll show you here in a minute. Okay. You have to design G of key to satisfy that requirement. But does everybody see what happens? I mean, it's the same logic, it's the same loop. Only thing is, it's I plus stride mod table capacity. And then here is, and to answer your question, actually, that's coming up. This is a common choice for a secondary hash function. Okay, so it's this is a common one. G of x equals p. Okay, p minus x mod p, where p is a prime number less than table dot cap. Think about this. What would happen if the stride was 0?
It wouldn't do it.
Yeah, it would keep probing at the exact same one. So you have to guarantee that stride's not 0. Are you with me? Okay. And furthermore, and you can see that this common choice for the secondary hash function, this g of x equals p minus x mod p, satisfies that. Because if p is what is the range of numbers x mod p? X mod p is between what and what? 0 and, no, well,
0.
what's the smallest it can be is 0, the largest it can be is what?
P.
No, x mod p cannot be p.
P minus 1.
P minus 1. Are you with me? So it's between 0 and p minus 1. Did you see that, and if it's p minus that guarantees that it won't be 0. It'll be between 1 and something. Are you with me? So that's the double hashing. That's how you do double hashing. So anyway, you know, we used to actually do open addressing. I mean, we could, if you're interested, you know, you could code this up and run some experiments. But in our project, we used chaining. But anyway, these are common, and there are other variations. There's lots of variations on the hash tables. Are so common, and there's lots of variations, and you have enough info now to where you can research this and see what all the ins and outs of the alternate ways of doing things. Yeah.
I don't know if this is really worth going over, but what's the...
I'm not showing you the efficiency of this. I'm not showing you the efficiency of these open addressing, but they have been analyzed. But the one thing that we do have to remember is what is the efficiency, or what is the runtime efficiency with chaining? Do you remember what that was? This is one thing we do need to know, because we're going to use this. You're going to use this to analyze in your paper. Do you remember what the chaining? Do you remember what the chaining was? The chaining theorem was? Yeah. Here, actually, this is a good question to lead into what you should investigate in your paper. So look, let's remember this: the hash chain performance theorem. Let alpha be the load factor of a hash table with chaining for collision resolution. The asymptotic runtime for an unsuccessful search is big theta of 1 plus alpha, and the asymptotic runtime for a successful search is big theta of 1 plus alpha also. Now, why do we have this 1 plus alpha? Why do we have this 1 plus? It's big theta of 1 plus, but do you remember what's the definition of alpha? Yeah, it is a number, but what is the definition? What is the definition of alpha?
Percent chance
What?
to change value.
It was something divided by something. It was n over what? N over k, where n is what? Yeah, yes, number loaded, and k is the what? Yeah, that's the table dot cap. They talk about slots, slots, buckets. The terminology for this stuff is kind of weird. They talk about slots and buckets, and there's lots of different variations. Like with some of them, they'll have 2 slots per bucket, so they'll actually reserve a pair because they figure that and then if both pairs are occupied, then it's a collision. So there's lots of different variations on this. But anyway, does everybody understand? This 1 plus n over k, where n is the number loaded and k is the capacity. And look, so why do we say 1 plus? Because I thought in the past we've always said, oh, 1 plus this is just n over k. Well, that assumes what? When is 1 plus n over k a big theta of n over k? That's if what? For what?
N is much bigger than k.
This whole thing has to be, in order to neglect this one, this whole thing has to be what? Bigger than 1. But you understand that normally, the normal scenario when you're using a hash table is to have lots of slots in the hash table that are unoccupied so that it can be approximately big theta of 1. So that means that you have to have a small percentage of the table occupied in order to get this performance very close to 1. So you see, that's why we don't...
Then you get a ton of wasted space.
I know, but that's a very good point. Look, you get a ton of wasted space. You know what that is? That is the what?
Space.
That is the space-time trade-off. That was a really good point. I'm glad you brought that up, because look, all that extra space is what gives you the big theta of 1, because you don't know ahead of time where these things are going to go. But if you have lots of space, the probability that you're going to get a collision is very low, and boom, that's what gives you the performance. It's like any kind of a service, you guys. Like if you have a service provider and you have like tellers, well, people don't go to banks anymore. Imagine that you have, or I know, a haircut. Let's suppose you have like, a shop, and you have, like 10 barber chairs, and you got 10 barbers, right? And what happens is, a lot of those barbers are not cutting hair. But man, anytime anyone goes in, boom, you can get someone. You know, you'd have to have like 10 people. You know, if you have 10 people getting a haircut and an 11th person comes in, you say, ah, well, shoot, that person has to wait, right? But as long as what? You have space, you have a lot more barbers than you expect customers at any one point in time. Everybody can get in what? Big theta of what? 1. So it's that space is what gives you the time. That vacant space is what guarantees you the performance. So that's space-time trade-off. That's what it is. So, you know, everything in life is a trade-off. There's no free lunch. Everything costs something, right? You have more space, less time, have less space, takes longer. Now, of course, what can happen is, with this big theta of 1 plus n over k, what would happen if this n over k, with chaining now, we can put more in than what the table can hold, right? Because we can just always get a collision and keep adding to the n. And so actually what does happen when n gets really, really big? This big theta of 1 plus n over k actually is what? Big theta of, ultimately, if you really overflowed your table a humongous amount, it would be big theta of what? N. Yeah. Because those chains would each be getting, you know, you'd have to go down n, you know, loop down to the chains. Does everybody see now? That's an important concept. Yeah.
But it'd still be like k times more efficient than if you had a linear list.
That is a very good point. If you just had one slot in the table and it was just a list, then it would be big theta of n, and the constant would be, this constant k would be 1. But if k is like 100, the constant does matter in practice. So, you know, if you had like 1,000 but you overflowed it, still that would be, you would still be saving time, right, by a factor of 1,000 actually. Yeah, so that's a good point. Yeah.
But in the big theta notation, we do not care about that.
Well, we just have to understand that in the big theta notation, the normal way we apply it is for large values of n. And if you have two different algorithms and both are big theta of n, then can one be consistently better than the other if they are both big theta of n? And the answer is yes. Then it does depend on the constant. Are you with me? If you're comparing two algorithms, each big theta of n, then the constants do matter. And this is an example of when it would. Yeah, these are all really good questions. So let me just say then that your next assignment is to start the paper. And what I would like to do now is go over the questions that your hash table paper should address. So first, let's remember that you need to have your hash table project pass the unit tests with the correct number of collisions, you know, the correct, all those numbers that came out. They have to be just like they are in the unit test, the number of comparisons, right? And the you know, when you print out the small ones with the dump of the hash table and you see the collisions, all those collisions all have to match. All right, because if you've implemented your algorithms correctly, then they should match that. And if you need solutions, then email me and I'll send you the solution. But they need to match. And also, of course, your list L. This uses list L, right? So anyway, now all of this information on these slides is all just verbatim from the assignment, the posted assignment. So you can just look that up. Either the slides are posted and then, but it's also on the assignment. So let's just walk through this. So the main program of the hash table project collects statistics from the search test, and what you're going to do is you're going to use that program as an experiment to investigate the performance of the hash table. Now here's the thing. And then write a paper and use the same format as in your sort paper. But now here's the thing, you guys. This one is going to be less directive, less specific. I don't have a process for you to, to say, take this data with this number, take this data with this number. Now you have the program. You've seen how it spits out that data. Now you decide what data to take. Are you with me? So this is, before I said, oh, take this data, and analyze it this way, and do this chart, and blah, blah, blah. Now this is more open-ended. Now you have to think about what it is that you're going to test and what data you're going to take in order to make your point, to answer these questions. All right? So that's slightly different. So I basically have 4 points that I would like for you to address in the paper. And now that we've been talking about this big theta of 1 plus alpha and all this stuff, we can, all this enters into these points. Okay, first of all, we've got different hash functions, right? So we have the effect of the hash function on the, we want to investigate the effect of the hash function on performance, Bernstein versus Knuth. That's point A. Point B is we want to, and we'll, in the following slides, we'll go over each one of these in more detail. And point number B is we want to see the effect of the capacity of the hash table on performance. All right? And then point number C is we want to investigate performance on tables with different capacities. And then the last one is we want to see the effect of the load factor on performance. All right? So let's take a look at each one of these in turn. Okay, so first of all, the effect of the hash function on performance. So the program asks you which hash function, and you've programmed the Knuth and the Bernstein. So the question is, which is the better hash function, Knuth or Bernstein? I don't know if it's Bernstein or Bernstein. I think I switched between. Anyway. And it might not be an either or. Yeah? It might be that under some conditions, one is better than the other, and under some other conditions, the other is better than the first. So see if you can see if there's a difference consistently, one way or another, under some certain conditions. So, how can you find that out? Well, you've got a tool here to take data, and it's a little experiment. So experiment and see which one is better, and if one is consistently, or, who knows? Only the shadow knows. Okay, the second question is, what is the effect of the capacity of the hash table on performance? All right. Now, the text that doesn't exist yet says that the divisor, the number of slots in the hash table, should be a prime number. Generally speaking, people like to use prime numbers for their hash table size. Right? That's kind of like a general, but not always, because we saw that if it is in fact an exact power of 2, what does that make it more efficient to do? Do you remember we said that if the hash table is exact power of 2, that if you mod it, you're basically just doing a what?
A shift?
No. A shift is to multiply. When if you mod a number by an exact power of 2, basically what are you doing?
You're like zeroing out.
Yes, you're zeroing out. You're just you're masking out. It's the same as masking out the high order bits. So you can do that very efficiently, right? So it might be an advantage to have a table to be an exact power 2. All right. So. So the text says it should be a prime number, and that a particularly bad performance can occur if the divisor is a power of 2. Can you find some non-prime numbers, specifically powers of 2, that give particularly bad performance? So see if you can, investigate that. See what you can come up with on that. right? And then continuing along these lines, it would be especially interesting to find a prime divisor that gives a particularly good performance and a divisor that differs from it by only just one that gives particularly poor performance. Do you see what I mean? Like, what if your table is like this big and it has, you know, really good performance, but it differs just by one. Boom! All of a sudden the performance is really bad. I mean, that would be pretty interesting, wouldn't you say? All right. Now, you guys know what a Mersenne prime is? Oh, did we do Mersenne primes? Yeah, okay, so anyway, a Mersenne prime is a prime of the form 2 to the n minus 1. 2 to the n minus 1. Okay, so a number of the form 2 to the n minus 1 is a Mersenne number. Not all Mersenne numbers are Mersenne primes, but some of them are. And look, if 2 to the n minus 1 is a prime number, that only differs by 1 from what? 2 to the n.
So we need to find numbers.
So see, I mean, check out Google. You know, check out Wikipedia. The Wikipedia. I've just Google Mersenne prime and find out about you know, you can get some Mersenne primes and figure that, you know, do a little research and right. So this is a good candidate for this question. All right. And also, by the way, you guys, what about the with this question, what about the difference between a Knuth and a Bernstein? Maybe it makes a difference with the Knuth, but not Bernstein, and maybe one's more sensitive to this than the other. Who knows? Yeah? See, aren't these interesting questions? Aren't you just aching to figure out what you're going to find out with this investigation? All right. Now, let me say right here, one more thing. This is what we just said. Is one of the hash functions better at hashing with hash tables having the number of slots of power 2? So this is comparing the two different hash functions under those conditions, right? Now, here's the thing, you guys. After you've done that, after you've answered those two questions, for parts C and D, you figure out which one is the best, right? I think you'll find that one of them will be consistently better than the other, maybe. But anyway, based on your results from A and B, use only the better hash function for your answers to the following questions. All right, so once we get to these next questions, don't mix in, you know, just pick one. In other words, have it be independent of the hash function. In other words, just use one hash function. Keep that variable constant in the discussion. So the part C is the effect of the capacity of the hash table on performance. Now so answer this question. Is it possible to have approximately the same load factor alpha with hash tables having different numbers of slots? Like, could you have don't blurt out the answer right now. But anyway, in other words, can you have a table with 1,000 slots have the same alpha as a table with 100 slots? Obviously. And would two such tables have about the same performance? But now you've got to be careful here, you guys, because what do you mean by performance? What does it mean? What does performance mean in terms of the end of the user of the table? So you got to be very careful. You need to think through what data you're going to take and how you're going to interpret it to answer that question. It's not immediately obvious. So that's going to require some thought, right? So now this last one is investigating this, big theta of 1 plus alpha, right, which is our theory. So how does the number of comparisons vary with the load factor in a table with a prime number of slots? So here you can do some graphing, right, and some tables. Okay, and keep in mind that in two extremes. First of all, keep in mind that in order to get behavior approximately 1 plus alpha, alpha has to be much less than 1. Okay, so see if that holds, you know. But then you can also really load it down and see if it goes linear, you know. So from your data, and then from your data, what value of alpha would you recommend for a good balance between storage requirement and speed of access? So you can recommend. You're doing a study for your boss, and he needs to recommend. You need to make some recommendations. So do this study and tell me what to do. All right. Now here's some guidelines that you want to be aware of. First of all, each of these questions should be answered by showing the data, making an assertion, and then backing it up with the data. All right, so you can't just say, well, don't just say this table shows, say this because this number is this and this number is this, therefore this. There's your conclusion. So your conclusion has to be based on the data. So show your data both in graphical and tabular form. And here's one that you guys, do you remember how many words there are in words.txt? There's like thousands, aren't there? Well, don't dink around with 10. You know what I'm saying? Don't dink around with small. You've got thousands of words. Don't mess around with tiny little examples to make your point when you've got this huge amount of data that you can process. So make maximum use of the many tables in words.txt. Don't investigate small hash tables when you can investigate large ones that would be more realistic in practice. Yeah? And then this very last one now is, I haven't shown it here on the slides, but if you go to assignment 19, I do have listed for you the sections that you need to, section 5, I don't know, 1.3, 1.4, they are, the basic organization is laid out of the paper, all right. So how to organize the paper is laid out. But how you answer all the stuff is way up to you. Yeah? I think this is actually going to be pretty interesting. I think, yeah, this is how performance research is done in computer science. Because we have a theory and we have a practice. Yeah? That's what makes it a science. It's based on math, right? It's based on all these math properties, growth, asymptotic growth, all that stuff. All right, good deal. So what we're going to do tomorrow, now like I say, for the rest of the week, nothing written, no written assignments. So what we're going to do tomorrow is we're going to start a new topic, which is going to be balanced trees. So I'll see you tomorrow.